So last time, we were talking about paths on a topological space. And we said the two paths are path homotopic if they are homotopic relative to the endpoints. All right, so what that means is that there is a homotopy of paths such that it starts at F and it ends at G, and relative to the endpoints means that the endpoints are fixed. They're always going to be whatever they've started at, right? And we're denoting this, just for emphasis, with a homotopic sub P. Okay? Then we talked about how this forms an equivalence relation, and we denote the equivalence classes of paths by P, curly P. We saw that concatenation is a partially defined associative operation, right? So whenever it makes sense, taking the product of three paths is independent of how you put parentheses. Yes?
Is it F0 sub 0 of 0 is F0?
F sub 0 is F, right? But F sub t has left endpoint fixed. It's always the same point. And the right endpoint is also fixed, right? That's what we mean by relative to the endpoints. Okay, we have a partially defined associative operation. It's partially defined because you can only concatenate if the right endpoint of this path is the same as the left endpoint of that path. Right, so that if you were drawing it, it makes sense that this one starts where that one ended. Right? So it's partially defined in that sense, but it does have, with the constant path identities, right? Plural because the constant path only can be composed with something that ends there or begins there, right? And of course we mean the homotopy class of the constant path. And the reverse path as an inverse. Right, and I put it in quotes because there's not a unique identity, so what do we mean by inverse? But of course what we mean is that you get an inverse on the left or the right. It just gives you the appropriate identity. Right? And then as a remark, this structure is called a groupoid. So this makes a groupoid, and it's called the fundamental groupoid. Right, now since we prefer groups over groupoids, mostly because we're familiar with them, we know what it means to compute a group. What we do is for each base point, we have pi1 of x naught, which is just the homotopy classes of paths whose endpoints, well, let's see, are both equal to x naught. So these are homotopy classes of loops based at the point x naught. Right? And if you specialize these properties to having fixed beginning and end point, you see that you get a group. Right? So this is called the fundamental group of X with base point X naught. Right, so so just to emphasize, each class in here is represented by a loop, which we think of as being defined on the interval, but just having the endpoints fixed at a given point. Right? And different representatives are connected continuously, keeping this condition fixed. The notation, pi1, as I mentioned, this is because there is a whole family of homotopy groups of a space. So not to keep you in suspense, pi k is going to be similarly defined using maps from the k-dimensional cube to X, right? Where what you want is the whole boundary gets mapped to this point, right? And then you look at continuous families, so homotopies, but the homotopy is fixed, is relative to the boundary. So all of the boundary always gets mapped to the single point x naught, right? So equivalently, if you take the cube and you identify all of the boundary to a point, you get a sphere, the appropriate dimension, right? And so it's just homotopy classes of maps from the circle, from S1, or from the k-dimensional sphere, Sk. Okay, but this is the fundamental group. We have one example so far, which is if X is convex subset of Euclidean space, then pi1 of x naught is 0. So by which we mean it's the trivial group, right? It's the group with a single element. So that element can be represented by the trivial loop based at x naught. So it's just a constant loop at x naught. So okay, that's our only example. And one property we proved is the base point doesn't matter. If your space is simply path connected. All right, more precisely, every path between 2 points induces an isomorphism between, well, the way we wrote it, the fundamental groups in that order. Right, but it doesn't matter. The point is, if you can connect 2 points with a path, then the fundamental groups based at those points are isomorphic. Okay, and then we mentioned that the next thing we're going to do is give an example of a non-trivial fundamental group. We're going to compute the fundamental group of the circle, and we're going to show that it's the integers. That's where we stopped last time. Questions on last time?
So if your space is Rn and you have, let's say you have one loop, or if you have a loop that wraps around twice, are those two the same?
They are homotopic, right? So you can transform one continuously to the other, right? And think about the loops as being our lassos, right? So we want to detect holes, so we throw a lasso and then we tighten it up, right? On our end, there's nothing for it to get stuck on. Right? So you'll just keep tightening and tightening until you just get the constant loop, right? And so yeah, on our end, there's just nothing for you to detect. More questions? Okay, so let's compute the fundamental group of the circle. Okay, so our aim is to compute the fundamental group of the circle. And because the circle's path connected, we typically leave out the base point from the notation. But you always want to have loops based at some point. So even if you don't include it, there is some point floating around, and all of the loops are based at that point, right? I mean, to start with, if you didn't, then you can't compose. You don't have concatenation, right? So you wouldn't have an operation. So we want to show that this is the same as the integers. And we have a plan, right? So the plan is, well, let's put this in R2. And then, okay, so there's the circle sitting in the plane. And our plan was to take the real line and have it sit above the circle, forming a helix, right? And then we want to study the map down, right? So this is going to be our example of a covering map. It's one of those sort of universal examples where a covering map, when we finally get around to a formal definition, is going to be something that behaves just like this, right? So what's special about this is that points are evenly covered. So every point has the same or an equivalent set of pre-images lying above it. And if you take a small enough open set around this point, then when you look above at the pre-images, I don't know, did I want that one? Let's ignore that one, so we don't worry about it, and focus at that one, right? So this interval has a pre-image over here, and a pre-image over here, and a pre-image over here, and a pre-image over there. And if you restrict attention to any one of these, then this map has an inverse, right? So this map restricts to any one of these intervals to be a homeomorphism down to this guy, right? And so we said last time, the way we're going to take a loop on the circle, and we're going to figure out like how many times you've gone around the circle, is we're going to take the loop, which is some map down here, and maybe it goes around positive order direction, maybe it goes in the negative, maybe it changes its mind. That's okay. What we can do is lift the path. So we pick any base point up here that sits above this one, and then we just start following the path. When the path goes like that, then, well, as long as it's in this neighborhood, the pre-image has to be in this neighborhood, and we have an inverse, so we can just lift and say, oh, well, it had to do that, right? And then, okay, it left this neighborhood, but we can do the same thing over here with some other interval and just lift the path, right? And so you do this little by little, and at every point, after you've chosen your base point, you have no choice left. Right? The path has a unique lift. When it finishes, it has to finish, since it was a loop down here, it has to finish at a pre-image of this point. Right? So maybe it finishes here, or maybe it finishes here. Right? But then we know, oh, well, this path went up one level, or it went up 2 levels, or something like that. And the number of levels that you went up or down, that gives you your integer. Okay? So that's the picture of the proof, and in a moment we'll write it down. Questions on what we're going to do? Okay, great. Okay, great. So now let's try to be a little more precise. So we're going to define our map to just take a real number and go around the circle, right? Thought of as sitting inside R2. And we're going to define omega n tilde is going to be a path in R with, let's say it just goes from 0 to n. And so if you do the composition of these two, which we're going to call omega n, you get a path in the circle, and we can write down a formula for it. It's just go around the circle n times at unit speed, well, at constant speed, rather. And whether you're going clockwise or counterclockwise depends on whether n is positive or negative. Right? And if n is 0, this is the constant loop. Does nothing. Right? So each of these is based, these are loops, based at the point 1, 0. Okay, so the claim is that the map from the integers to pi 1 of the circle with base point 1, 0, call it capital phi, that takes n and gives you the homotopy class of omega n is a group isomorphism. Okay, so coming back to the picture, this map goes the other way. Instead of taking a loop down here and lifting it up, we're saying look up here and look at all of the paths that just go at constant speed from 0, which is one of these preimages, to any other of the preimages, right? And project those down. Those give you loops. And saying that this is an isomorphism says that every loop on the circle is homotopic to the projection of one of these paths. Right? And moreover, it says that this is a group isomorphism, so that addition in the integers, which just means going up or down one number of levels and then up or down the next number of levels, corresponds to group concatenation, loop concatenation down here. Okay? Okay. So the first thing we're going to note is that there's the only important property that these paths have is where they begin and where they end. Right? So remember that R is convex, and so any two paths are homotopic, path homotopic, as long as they begin and end at the same points. Right? So note that if f tilde is any path in R, that begins at 0 and ends at n, then let's say directly, the conclusion is that if you compose it with p, you get a loop based at 0, 1, and that is path homotopic to the one we're looking at. Right? And the reason is that we know there is a homotopy call it f tilde t with f tilde 0 equal to f tilde 1 equal to omega n tilde, and fixed endpoints. So f tilde of 0 is 0, and ft tilde of 1 is always n. Right? Because R is convex, and so you can just take the convex combination of the two paths, and then just projecting that down, this is a path homotopy between p composed with f tilde and p composed with omega n tilde, which is omega n. Okay? So the only thing that mattered about omega n tilde in our definition of phi is that it goes from 0 to n. Okay, so let's check that phi is a group homomorphism. So let tau m from R to R just be translation. So take a point S and translate it by m. Right? Then if you do omega m tilde, this is a path that begins at 0 and ends at m. So I can concatenate it with tau m omega n tilde, because that is a path that begins at m and ends at m plus n. Right? But all that matters is it begins at m, which is why we translate it. Right? This is a path from 0 to m plus n. So by what we just showed, the homotopy class, well, let's say phi of m plus n, which is the homotopy class of omega m plus n, is equal to the homotopy class of p composed with this path, because it goes from 0 to m plus n. Right? But when you project down, translating by m doesn't do anything. Right? It sends 0 to 0. And so when you project this down, this is do omega m and concatenate with omega n, which is omega m concatenated with omega n, which is phi of m concatenated with phi of n. Right? And so we have a group homomorphism. Right? Concatenating paths upstairs gives us concatenation downstairs. The only trick was that we needed to translate the path upstairs so that we could concatenate it. Okay? So far, so good? So now we just need to check that it's a bijection. Isn't it? Okay, so here are two facts. About P, this projection map, that are going to let us prove that it's a bijection. Right? First, every path on the circle has a unique lift to a path on the real line as soon as you fix the base point. Right? So if f circle is a path with f of 0 equal to x naught, and you pick a lift, x naught tilde is anything lying above x naught, there is a unique lift of f to a path on R such that f tilde of 0 is equal to x naught tilde. Okay? So we have R projects down to S1. We have the interval. We have a map into here, F. And the claim is that you can always lift it. And your only choice is where do you lift the left endpoint. Okay? And you can see why we call it a lift. Okay? And the second fact is that the same is true for homotopies. Right? Given a homotopy, let's say a path homotopy, at the circle with the left endpoint fixed, say x naught, and a choice of lift of the base point, there is a unique lift. To a homotopy upstairs. So ft tilde from 0, 1 to R with ft tilde of 0, x 0 tilde. Right? So again, you have a path homotopy. All of these start out at the same point. Then as soon as you choose where you're going to take that point upstairs, then there's a unique way of lifting the whole homotopy, right? So this is just like we were saying when we were staring at the picture. As soon as you choose where 0 goes, then that's it. You don't have any more choices. There's a unique lift. Okay? Okay, so these are two facts, by which I mean we're going to get around to proving them in a moment. But just assuming these facts, let's show that phi is a bijection. So let's start with surjective. Okay, so given an element of the fundamental group of the circle based at 1, 0, we lift it, right? We use fact A gives us a unique lift f tilde from 0, 1 to R such that f tilde of 0 is 0, right? So here we're making a choice, right? So 0 is our x naught tilde, 1, 0 is equal to x naught, and the projection maps 0 down to 1, 0 as it should. So p of 0. Okay, everybody happy so far? All right, so we start with an element of the fundamental group. we have a path representing it. It's a loop, but that's okay. It's a path representing it. And then fact A gives us a lift. Right. Now we know that the original path was a loop. So we know, okay, so we know it's a lift. That means that if you compose it with P, you get back the path you started with. So P of F tilde of 1 is equal to F of 1, which is equal to F of 0. Right, so F tilde of 1 is in the inverse image of 1, 0, which is precisely the integers. Right? So say F tilde of 1 equals n, right? It's some integer. Right? Okay, well then by what we saw at the beginning of the proof, the homotopy class of P composed with F tilde, which is the homotopy class of F, is the same as the homotopy class of omega sub n, because F tilde is a path in R that goes from 0 and ends at n. And this is in the image of phi. Okay, so phi is surjective. Okay. The facts also, in fact, fact B gives us that phi is injective. Right? So as usual, you want to show it's injective, so you assume that two images coincide. Right? So it's the same as saying that the homotopy class of omega m is the same as the homotopy class of omega n, and that's the same as saying that there is a homotopy between them. Right? There is a path homotopy Ft on the circle such that F sub 0 is omega m and F1 is omega n. Okay, so now you have a homotopy on the circle. Fact B says that you can take this homotopy and lift it to a homotopy in R, and it's unique as soon as you pick where you're going to send the base point. We'll send the base point to 0. So by fact B, there is a unique lift, Ft tilde, 0, 1 to R, such that, so we fix the base point as 0, and it's lift, right? Well, so it's a lift, right? So lift means that P composed with Ft tilde is equal to Ft. Okay, but this is a path homotopy. Tilde is a path homotopy. So Ft tilde of 1 is equal to F0 tilde of 1, which is m, right? Because that's where omega m tilde ends. And it's also equal to F1 tilde of 1, which is equal to n, right? Because that's where any lift of omega n tilde ends. Right? And so m is equal to n, and phi is injective. Okay, so given these facts, we have the proof. Okay, questions? Okay, so we just need to establish those facts. So to establish the facts, we're going to make a more complicated statement that includes both of them, so we only have one statement to prove. Right? So here's the claim. For any y, given a map capital F from y cross the interval to S1 and a lift F tilde defined only at the left endpoint of the interval. Right? This is a lift of F restricted to the left endpoint. Right? So as soon as you choose how you're going to lift y cross the left endpoint, then that's it. You have no more choices. There is a unique lift of the rest. Unique map F tilde from y across the interval to R extending the given lift. Kasune on y cross 0 such that P composed with F tilde is equal to F. So it's a lift of F. Okay, so that's our more complicated statement. This will imply fact A by taking y to be a point, so that you're just lifting a path. And it'll imply fact B by taking y to be the interval, so that you're lifting a homotopy. Right? Just notice that you're lifting the constant loops at the endpoints to see that you get a path homotopy upstairs. Okay, so this claim is strong enough to give us both facts. Okay, and here's the property we want to use about the projection to prove the claim. Right? So the okay. So there is a cover, an open cover, of S1 such that P restricted to the inverse image, no. If U alpha tilde is a connected component of the inverse image of U alpha, then P restricted to a map between U alpha tilde and U alpha is a homeomorphism. Okay, so again, for the picture, right? You pick a point, and you look at the pre-images, and if you pick a small enough neighborhood here, then every one of these points has a lift of that neighborhood. And if you restrict your map to one of these neighborhoods, then you have a homeomorphism between them, right? So you have a continuous inverse. OK, so that's the property. Of course, that's really easy to arrange. Just take any two open intervals that don't contain, just make sure you don't contain antipodal points. But actually, you could take even larger. Just don't have the whole circle, right? And then you'll have homeomorphisms going down. Right, but we're stating this in a way that will include more general covering spaces later. All right, so proof of claim. OK, so we have y cross 0, and it's sitting inside y cross 0, 1. We have a map to S1 here, and a map to R here. F, and this is an F tilde. And we want to extend F tilde from the left endpoint to all of y cross 0, 1, right? So we want an arrow there that makes everything commute. Yes?
By the way, is that some sort of fancy U, or is that just how you write a capital U?
That's how I write a capital U.
Okay, just making
Yeah.
sure that we
Yes.
don't like doing like a script U or anything.
No, but feel free to. OK, so here's the situation. We have the drawn-in arrows. We want the dotted arrow. And the thing we have to work with is this fact about the covering map. OK, so we're going to extend this F tilde to larger and larger subsets of this. OK, so we're going to do this in 3 steps. So, well.
In your assumption, on the left.
Well, the claim is that there is such a cover.
Yeah, but OK, maybe that's enough. I thought maybe you want.
It's possible I do, but I think I'm OK with just connected. Yeah, let's keep that in mind. See if I missed it. OK, so first, for each y naught in y, there is an extension of this F tilde to n cross 0, 1 with n some neighborhood. Of y naught. OK, so at the moment, we're going to focus on each individual point in y and just construct an extension to a neighborhood of that point across the interval. And in principle, so far, when we're done with this, they might not coincide on overlaps. So we're going to worry about that. But we're going to have some extension. Okay. Great. So we're going to take a partition. So here, make sure I don't skip anything. So by continuity of f, each point y naught comma t has a product neighborhood call it n sub t cross atbt such that f of this sits inside u alpha for some alpha. Right? So by continuity, the inverse image of this is some open set. By definition of the product topology, you can pick an open subset of product type. Then use compactness. Of the interval to cover y naught across the interval with finitely many such sets. Right, and then by choosing the intersection over the finitely many n sub t's, we can assume that there's a single neighborhood of y naught. And then a partition of the interval such that for each I, f of n cross ti minus 1 ti sits inside some u alpha, which will denote u sub I. Okay, so assume inductively that f tilde has been defined all the way to ti minus 1. Right, so initially, of course, take ti minus 1 to be t0, so just 0. Then possibly shrinking n we can assume that f tilde of n cross ti minus 1. No, ti minus, right. So, I don't want to shrink n yet, sorry. Okay, so f tilde of y naught ti minus 1. In terms of this notation, this is contained in ui tilde, where ui tilde is some connected component.
Can you
It's an element, thank you. Is some connected component of the preimage of ui. Right, because we know that it is, I minus 1. Either one, actually. I is fine, yeah. Right, so we know that the endpoint lands in here, and so the lift, which has already been constructed, has to lie in one of the connected components of the preimage. Right, so denote that connected component ui tilde. Yes.
I'm just a little lost. Can you
Sure.
explain what this claim is going to do?
Yeah. So we proved that the fundamental group is the integers, as long as we know how to lift paths and lift homotopies. Right. So to prove both of those at the same time, we decided to make a stronger claim, right, where we just put an arbitrary space y. And really, for this proof, we just need the case y equals a point or y equals the interval. Right? So y equals the point gives you lift of paths, and y equals the interval gives you the lift of homotopies. Right? So we're going to prove this stronger claim from this fundamental fact about the projection. Right? That in little pieces, you have an inverse. Right? So that's what we're doing. Right? But so to do that, we're first extending near each point in y. You have the interval, right? And so that's a nice compact set. And so we're using that compactness to get a finite cover and to define the lift in finitely many steps, right? So that's the step we're in now. Then we'll point out that by uniqueness, these actually match on overlaps, so that we've extended the whole thing. Right? But the idea is first extend it just near one point.
You first proving part A.
Well, yeah, exactly. First we're proving part A, then we'll prove uniqueness of part A, but then we'll point out that that gives everything. Yeah, because we're doing part A, but with a neighborhood, so it's extended a little bit. Okay. Perfect. So that's what we're doing, and so we assume that we've done the lift up to some place, and then the idea is in the picture. Well, once you get here, you're inside some neighborhood, and you know how to lift in that neighborhood, and so you can just keep going. Right? Okay. Right, okay, so here's where we shrink. So by potentially shrinking n, we can assume that f tilde, not just of y naught cross ti, but all of n, y minus 1, sits inside ui tilde. Right, so we have a given ui tilde just by seeing where the lift ended, and we can arrange for the whole open set to get mapped into there by possibly shrinking the open set. So we define f tilde on n cross ti minus 1 ti as the composition of f with the inverse of p from ui to ui tilde. Right? So again, it's a sort of proof that it's really easy to just point at the picture and explain what you're going to do, but then writing it out takes a while. Okay, so this completes the inductive step.
How do we know that when we put these together with the previous function, it's a function? So previously it was unique.
Sorry, how do we know?
How do we know that this piece that
Uh-huh.
was defined, we put it together together with the previous inductive piece that we had defined.
Uh-huh.
And on the overlap, they coincide with what they're doing.
Well, because we have this P inverse, right?
But maybe for the other thing, you had defined it differently. Like for the previous inductive step, it was not unique definition, and you had two choices, and you chose the wrong one somehow. I mean, maybe inductive assumption should include uniqueness, is what I'm suggesting.
Well, so let's see. Where am I making a choice? I have this cover, and on each one I have this P inverse, and you just once you're inside the open set, then you have P inverse, right? And so on overlapping sets, yeah, P is a local homeomorphism. So on overlapping sets, it has to be compatible, right? You can't, P inverse can't jump on a path.
Oh, right. Why can't it?
Well, because it's a local homeomorphism, because it always has a locally defined inverse.
No, I guess my question is, how do you know that you had used that local homeomorphism and not like some other local homeomorphism in defining the previous map, the previous inductive step map?
Well, but hold on, you're just worried. So you're saying, how do I know that when I continue f here, that it's still continuous, right?
Yes, or no, even defines a function.
Well, I mean, it defines a function because I'm telling you what to assign to each point.
Okay, yes. So then I'm worried about continuity, I guess. Okay, because, you define the function because you defined it on a disjoint set.
Yeah, if you like. Yeah, exactly.
There's no overlapping.
The overlap is just the endpoint, and at the endpoint they coincide. That's right. And so that's how I know they're continuous, and it's defined because I just told you what to put at each point. Right. We'll address uniqueness in a moment, but I think it is well defined.
It's well defined. And what about continuity?
Well, continuity, yeah, I just need to worry about the endpoints.
It's like endpoints cross the neighbor.
Right, n cross the endpoint here, the ti minus 1. And there they do coincide.
Okay.
Right. Okay, great, thank you. So this completes the induction and gives us a lift on all of n cross the interval. Okay? So step 2 is uniqueness when y is a point. Okay, so it's enough to prove uniqueness. Well, as we will see, it is enough to prove uniqueness when y is a point. Okay, so y is a point, so we'll just remove from notation. Okay, so assume that you have f from 0, 1 to S1 and 2 lifts. F tilde and F tilde prime. Both are maps from 0, 1 to R such that they coincide at the left endpoint. Right? So we're going to show that then they have to coincide everywhere. And of course, the point is, as we were saying at the beginning, that as soon as you've chosen the lift of your base point, you don't have any choices left. You always have to just do what P inverse tells you to do. Right? Okay, so choose the partition. With F mapping each Ti plus 1 into Ui. Assume inductively that F tilde coincides with F tilde prime on 0 to Ti. Okay, so by connectedness, F tilde of Ti plus 1 is a subset of a connected component Ui tilde of P inverse of Ui. Right. So this is a connected set. F tilde is a continuous function, so its image is a connected set. So it has to lie inside some connected component. Right. Similarly, F tilde prime of Ti plus 1 is a subset of a connected component. And since they coincide, F tilde of Ti is equal to F tilde prime of Ti, it's the same connected component. Ui tilde. Right? So whatever connected component F tilde is landing in, F tilde prime is landing in the same one. Okay? Now, as a map, from Ui tilde to Ui, P is injective. Right? And so from P composed with F tilde equal to P composed with F tilde prime, we conclude and F tilde and F tilde prime are the same on Ti plus 1. Right? And so, so by induction, they coincide on the entire interval. Okay. Great. So finally, step 3. Is the final proof of the claim. So, which I guess I've erased. I've erased. The final proof. So we can construct F tilde on an open cover of y cross the interval, right? Because for every point in y, we know we can construct it on a neighborhood of that y cross the interval, right? So we know we've constructed F tilde on such an open cover, and by uniqueness, well, let's say by part 2, if you have a y 0 in two, well, if y0 cross 0, 1 is in two of these sets, I should say here, we have like an open cover of y cross 0, 1. So for every open set in y, cross the interval, right? So that's why I'm looking at a single point in y cross the interval. If it's in two of these, then the lifts of tilde coincide. So all of these lifts fit together compatibly to a map f tilde from y cross 0, 1 to R, right? And it's continuous because it's continuous on every set of the form n cross 0, 1. Okay, so that proves the claim. Okay, questions on this? Okay, so the proof is structured like this because there's the part at the beginning that was very clear you should not lose sight of, right? And that motivated having to prove the claim and having to do this argument, right? Poincaré, who we mentioned the first class, has this great phrase where he defines geometry as the art of making precise arguments from imprecise pictures. Right, so making the argument from the picture precise sometimes takes a lot longer than just staring at the picture. Okay, questions on this proof? Okay, so we finally have an example where the fundamental group is not trivial, right? So it is actually finding something. 1042.
I guess connectedness only was enough because all we needed is something to imply it, and half connectedness, which is what we had, implies connectedness.
That's right. Exactly. Yeah. Uh-huh. Okay. Excellent. So there are many immediate applications that you can get from just knowing the fundamental group of the circle, right? So the next thing we're going to show is that the fundamental theorem of algebra follows from the fact that this is non-trivial. And then we'll prove the Brouwer fixed point theorem, which is wonderful because fixed point theorems are how you actually prove that things exist in analysis. And so it's great. Anytime you can prove a fixed point theorem, you have a really strong tool. But since there are only 8 minutes left, we will stop there today and continue on Thursday.